Any questions while we got a couple of minutes? Question up front here.
What's the difference between an halide shift and an alkyl shift?
What's the difference between a halide shift and alkyl shift? Where have you seen a halide shift?
Or hydride, yeah. When I was doing my notes, I wrote it down and I was like, I don't know.
Okay, hydride.
Yeah.
The difference between a hydride shift and an alkyl shift? There's really no difference. Hydride shift, the H and the two electrons are moving over. And an alkyl and the two electrons are moving over. Alkyl would be a carbon group, methyl, propyl, butyl, etc. But fundamentally, there's no difference. The two electrons are moving over to create a new cation. Remember, instead of bonding here, it's like, see you later, I'm going to go bond over here. Other questions? There was another question.
Right?
Here? Question?
Yeah. When in the synthesis of cyclopropane via carbenes, if it's like CHCl3 and then it's KOH, will the extra Cl on the CHCl3 combine with the K and then forms KCl as also a product?
Yeah.
Okay.
I mean, those are basically your spectator ions. Well, I mean, Cl minus. Yeah, certainly.
Okay.
I mean, if you completely balance it, you'd have probably KCl form. Other question? We didn't do that one in class? No. Yeah. Let me see. Kind of remind me if I did. I'll see if we can do that one. There's really no stereochemistry. It's going to be racemic. It's going to be both. There's no defined relative stereochemistry. Kingsley? Okay, it's time to get started. Kingsley? I can't see it.
1,3 methyl should be more. Wouldn't a 1,3 methyl should be more stable because.
Which reaction?
7 to 6.
Yeah.
Ring contraction.
The ring contraction.
Ring contraction. We did that one in class on Tuesday, right?
Yeah. I had a question about it. But this is a cyclopentane. This cyclopentane has bonding of 108. And cyclohexane has bonding of 120.
Show it to me after class or something. It's kind of a specific question. Let's talk together, and we'll see if everybody else needs to hear about it later. Okay. We need to get going. Okay. We're down here in Roman numeral 2. We looked at adding halogen X2 to an alkene. We looked at halogen water gives a halohydrin. That's a peroxy acid. What does that give? Oxide. Okay. Also known as an oxirane. We're writing here. A number of these cases, like I don't know if it says it there, but okay, it does say it here. When product is power, only one enantiomer has been shown. For example, here I could say plus enantiomer. We haven't covered that yet, but as you look at that later on, don't wonder, hey, what about the other enantiomer? So I did write that. That's pretty much with all these, plus enantiomer. That's what that means. What is that? Diazomethane. What does it do to alkenes? Cyclopropane. That's where we ended last time, yeah? You heat diazomethane, it eliminates nitrogen and forms the CH2 carbene. Carbene is a divalent carbon. Divalent means it has two bonds. And a lone pair, it's net neutral. So it is neutral, but its reactive species Pi bond attacks the carbon, at the same time the carbon back bonds, boom, there's your cyclopropane, no intermediate. Let's see here, cyclopropanes. That was up top. A more convenient way to make cyclopropanes is using chloroform hydroxide. This is going to give a dichlorocarbene cyclopropane though. Obviously, we've got two chlorines here. The diazomethane is explosive, hard to work with. This is something where a bit easier to handle. The first step down here is the hydroxide acts as a base and takes a proton from chloroform. This is your standard acid-base mechanism that we looked at, 3 or 4 weeks ago, right? Base takes the H, these electrons move on to carbon. What does all this mean? We're making water right there. And what does this arrow mean? Electrons moving on to carbon, there's the lone pair. And it's a minus charge, you're giving 2 charges. So we get that species formed. That's a lot like the original diazomethane. The carbon with a lone pair and a minus. What happened up there? The nitrogen left. Well, here the chlorine will leave. Chlorine leaves, takes its 2 electrons with it. What do you get? We now have the carbon, the lone pair, and only 2 bonds. That's actually a neutral carbon now. Okay? That's a carbene, dichlorocarbene. A lot of people like to show plus and minus charge to illustrate the dual character. And when the chlorine left, we've got Cl minus. Cl minus is very happy to leave and exist on its own. Just like nitrogen is very eager to leave and exist on its own. One molecule going to 2 is driven by entropy. Basically, this leads to formation of the dichlorocarbene. At this point, pi bond attacks the empty p orbital. This is sp2 with empty p orbital. So boom, we get cation here if it was formed, but it's not really formed as it, because at the same time, this back bonds. And when all that happens, all right, that's not really formed, is it? Because as soon as this is formed, that's happening. This is concerted at the same time. And so we get this bond and that bond made at the same time, and lo and behold, it's a cyclopropane, a dichlorocyclopropane. And that's the product you can get by treating an alkene with chloroform and hydroxide. Questions about that mechanism? Carbene mechanism. Make sense? Consistent with the above mechanism, also very consistent with all of our other alkene reactions. Yeah? Back bonding. Question?
So stereochemistry she's not showing that, but like the things that are bind to the carbon, they're either both forward or both back, right?
Okay. Well, first of all, a tetrahedral carbon is always tetrahedral, even though we don't show it like that. That carbon is tetrahedral.
Yeah.
All right? That means there's 2 in the plane, 1 forward, 1 back. So I'm not showing it.
Yeah.
All right? But it doesn't really matter. We're going to have to learn when it's important to show it, when it's not. It's only going to be important when you got 4 different things on the carbon. There's not 4 different things on that carbon. I mean, 2 are the same. Here, there's not 4 different things on that carbon. There's not 4 different things on that carbon because there's 2 H's, which are the same. So you really don't need to show it. You can put either one forward, either one back. It doesn't matter. So yes, tetrahedral carbons are always tetrahedral. But we don't always show them. Sure. Sure. I mean, on week 1, we'd say, what's the hybridization of that carbon? sp3. Because it has 4 bonds around it. All right, what's the bond angles of sp3? Tetrahedral. Okay? I'm just not showing the full tetrahedral nature. But that's common, you know. Why is the bond what?
I thought the smaller rings were stressed.
Well, that bond angle there is, from 9th grade geometry, 60 degrees. But that carbon wants to be 1 and 9.5. So we're pushing it together, and that leads to bond strain. Cyclopropane is a strained ring, but you can form them. And they're actually in a lot of drugs. As I mentioned before, I'd like to eventually one day write a little short paper about drugs that contain cyclopropane rings. I've got a list of about 30 or 40. That's a good question. I'm trying to find information about that. It's not very clear. Nobody's ever really said, hey, cyclopropanes are very prevalent and this is why. It's not there.
Okay, so bonding between the CL and the CL is 109.5.
Sure, that's 109.5. Yeah. True bonding. Let's see, predict the products. Okay, whenever you predict the products, there's a couple of ways to approach it. I mean, something like this can go on a note card, okay? In the back, you can show your product. Okay, here, I may have done this before, but here we go. Approaching, my main functional group here is this alkene. Organic 1, we don't do any chemistry with benzene rings. So we've got an alkene. Alkane carbons are not reactive. You can burn them, we showed that, but okay, your alkene here. Your reagent here is diazomethane. Okay, there is a little bit of memorization in organic chemistry, although you don't want to do that a lot. But you memorize what does an alkene and a diazomethane give? Cyclopropane. Boom, there you go, something for a note card. Then you think about mechanism. What's the reactive intermediate that's going to form from the diazomethane?
There's no intermediate.
Well, there's no intermediate in when this reacts with this. But what does this form?
Nitrogen, diatomic nitrogen.
The main thing is carbene. Okay, so that's the next thing you need to know, carbene. But and then the carbene, once you get it formed, it reacts here. But you got two mechanisms. This forming the carbene, that's just the expulsion of the nitrogen to form the carbene, original Lewis structure. But then your mechanism. And that's something you don't really memorize. That's something you know fundamentally how electrons move. And if you just to show that, you could show the mechanism. But in terms of, go ahead.
Do you always want to show the function of
That depends on what you're asked. If you're asked to show the product here, you don't have to show anything other than the product. What I'm getting at is your thought process, you probably want to think carbene, show that on your scratch paper. Right? Here, predict the product. Predict the product is, what are we going to turn this into, basically? Cyclopropane. Okay. We're going to have to do stereochemistry here. Why? Because if I just make this cyclopropane, I'll just do that. This is just CH2 cyclopropane. This carbon has ethyl, and this carbon has that. That used to be pi bond, but now we have a cyclopropane there.
Sorry, I got excited.
Problem is, in this example, that's a chiral carbon. That is, it has 4 different things attached. It has the ethyl, it has a carbon with a group, it has a carbon with no group, and it has an H. We really need to show the stereochemistry there. We also really need to show it there, both here. I'm going to have to just show you this. We'll come back to more examples like this. It's easier to do with a ring at this point, down here. All right, here we go. Whenever you have these that are acyclic, I would turn these first. I'm going to have to repeat this next week. I'm going to do it today. I'll repeat it next week. Hopefully it will sink in. Turn this first. Instead of like this, pretend this is on the board here flat, because that's flat right here, and the phenol's going up. Let's turn it so it's on the board like this, and this group is coming out at you. Okay? I'm just turning it. And I can redraw that sort of like, and I'm going to make that flat. I'm going to make this as it's coming out at you. Now that's going up. I don't have enough fingers. Really, I need to turn this. I don't have enough. I'm turning it like this. This is actually going to go back. All I did is turn this. Does everybody agree that this is trans about the double bond? Yeah, that's trans. It's still trans. Okay? I've just got it in sort of on the board like this, trans. I've turned it. And so now trans is forward or back. It's the same thing. Same compound. Now, what does the reagent do to this question?
Why is it trans without the double bond? Is that just
Have you watched the nomenclature video?
yeah? Oh, that's why.
I mean, one of them is up, one of them is
Okay.
down. Trans about the double bond.
None of them are together.
Okay. What does the reagent do? And basically, you get rid of the pi bond, and what does this become right here?
Like a triangle.
Yeah, the cyclopropane. So I'm just going to get rid of it and make it like that. Okay? And I didn't redraw it, so I'm just going to say, there's your product. Okay? See, when I turn this thing, this is sort of flat on the board like this. Well, let's draw it here. Then I can turn the board. Let's draw it here. And I'm going to make it flat. Okay? And there's the phenyl. That's that, if you can't see it. This is here. Okay? But there it is on the board. See the phenyl coming down? Now, when I turn it flat, where's this at compared to the alkenes in the middle? Now, if I do it like this, where's this group now? It's coming towards you. You can't see the paper, but in this group, when I turn it flat, it's going back compared to the alkene in the middle. Well, that's just the way I got it now. But that's the face. Now the face is, what happens is, the reagent's coming by the carbene, the pi bond comes up and attacks the carbon. At the same time, the carbon back bonds, and you end up with a carbon straight up. But it can also happen this way. The CH2 can be down here, the pi bond attacks the carbon back bonds, and you get the bond straight down. So you also get the enantiomer. You also get, I'm going to start with the same thing. And all you got to do is erase the pi bond and do it like this. And this is your two products. These are enantiomers, which means mirror image to us right now. You get the mirror image because the reagent can come from the bottom face or the top face. Or if you had it like this, it could come from the front face or the back face. If it came from the front face, I'd have to draw the new things front. If it came from the back face, I'd have to draw the new bonds back. I don't recommend doing this. To me, it's easier to turn this first, draw your new stuff up or down. We'll do more examples of this later, next week. I went ahead and did it now because it's here. Question?
When you hinge the double bond, it's not really just like this, so it could have gone the other way as well.
Sure.
Okay.
I mean, I turned it this way. You could have turned it that
No, I
way.
mean, when you, in the very first step, when you hinge the bond itself, if you hinge the bond down rather than hinging it up, wouldn't that create more icebergs?
No, it would create these two. You would just have. No. Do it. Show it to me, and you can turn it either way. Turn it that way. Turn it this way. This group comes forward. Turn it this way. That group goes back. You're going to get the same thing. Again, do it. Show it to me. The one down below is easier because the one below, I would keep the ring. I put the new stuff into play. First off, okay, a little bit of prompting. What does chloroform KOH do to alkene? What does this give? What are we making here? Dichlorocarbene. Dichlorocyclopropane. All right, so this is going to be like this. We're going to connect here and here. I'm going to erase it and then draw it and then erase it. We're going to get this with a methyl there, and there's two chlorines here. All right, hold on, don't draw this yet. Problem is, these two carbons are tetrahedral, and we need to show that here because there's 4 different things attached there and there. We got to show something forward and back, just like we showed here, something forward and back. Here, I would do the new things forward and back. Let's put the two bonds either forward or back. Now tell me. Let's do this one forward. If this one's forward, how is this one? Forward. It has to be forward, yes. You you can't have a 3-member ring strand. If this is 1, 2, and 3, these have to be on the same side if these are going to bond to make a 3-member ring. If they were opposite, they couldn't bond. The only reason it's forward is because if we call this flat on the board, and that's all trigonal planar and it's planar, the reagent can be in the front. That is, the pi bonds attack the carbon and then it back bonds, and both of these bonds would be forward. But guess what it can also do? It can approach from the back. And so you also get, hold on, I got 3 in a plane, 1 forward. The methyl here is what?
Back.
Yeah, the methyl here, let's make it back. It gets pushed back when the reagent comes in. See, at the beginning it's like this. But as that reagent comes in, the methyl gets pushed back to make room for the... The other is going to be where the reagent comes in from the back. And you get that. And those two are mirror images. Those two are enantiomers. Again, half of this is sort of premature. But what I want you to see is the idea that when you got this planar face, the reagent attacks from both sides. And this leads to the stereochemistry. You have 2 new tetrahedral carbons here. Because here they were planar, but now they're tetrahedral. And here we need to show the stereochemistry. Question?
So that tetrahedral carbon that's bound to the chlorine. So a normal tetrahedron has like 2 in the plane, 1 forward, 1 back. That has 2 forward, right? And the other enantiomer has 2 back.
Yeah, but this is a different plane.
Oh, okay.
Because, I mean, they're both forward, but the plane is not the same plane as over here.
Oh, okay.
You got to consider
Orientation.
a different plane there. So I can show you any tetrahedral and have 2 bonds like that.
Yeah.
It's just the other ones are going to be, well, actually these are forward.
Yep.
But you can look at any 2 bonds and see that same.
Okay.
Okay. So half of that, the stereochemistry there is a little bit premature. We'll revisit that next week and look the week after. Main thing there is predicting products. At this point, realizing we do have some stereochemistry you need to be thinking about. How the reagent approaches the planar alkene. Here's actually a list of some drugs that have cyclopropanes. This is a couple of years old. My page now has about 3 times the amount of drugs. Here's a miscellaneous tidbit about carbines. We can take a look at. This is metabolism of a drug. And these folks believe that a carbene is formed during the metabolism. Carbines tend to be very reactive because they don't have an octet. They're very electrophilic, very reactive. And this might lead to toxicity, but this talks about it and how they're using deuterium to keep this from happening. The deuterium is something we'll be looking at during test 3, deuterium isotope effect. So there's sort of 2 things there. Ultimately, though, it's an application of some of the things we're talking about. This stuff doesn't just live in the textbook and never come out, right? This doesn't sit on the shelf in the library for 100 years. What's after cyclopropanes? Okay, we have 2 major reactions left. Both of these, before we look at reagents, what do? Alkene is converted to what?
Alcohol.
Actually an alcohol. Where there's a new H there and an OH there, and there's water added across the double bond. We've already seen how to make an alcohol from an alkene using like sulfuric acid. We did it in the lab last week. And what's the last reaction? What does it do? Another alcohol. The new H is up there. And there's your water. Because there's no H there, but now there's one. But you'll notice there's a different orientation of the H versus the OH. This looks like a kind of a standard product. The same product we would get if we did just H3O+. Does that look like the same product? Because if we did H3O+, what would the alkene attack? H+. And would you make cation at top or bottom? Top. You have a new H added there, cation at the top. Then what would add to the cation? Water. So you get an oxygen bonding up there, then you lose an H, and you'd have an OH there and an H here. That's what we got to. You see? This is mercury, by the way. This and H3O+ gives the same product. This up here is sort of the reversal of that regiochemistry, where somehow the OH ends up down here. Right? But you're not going to make a cation down there, are you?
No, you can't.
When this reacts to the H+, cation up here, and the water up there. This is the standard product that comes from your understanding your carbocation chemistry. This standard product is called a Markovnikov product. Markovnikov. I don't like to use this term, but you do need to know what it means. Chemist a while back, either French or Russian or something, I can't remember. Where the nucleophile ends up on what type of carbon? Tertiary. The more substituted. Why does it end up there? Because that's where the cation would be. That's sort of your standard Markovnikov reaction product. This one's called a what? Non-Markovnikov. It's atypical. It's like, how'd you get OH there? That's not where cation should be. So that's what the Markovnikov terms. And I bet you a steak dinner that those terms are in your textbook. Well, good. I'll eat for two. Okay. This reaction is called oxymercuration. There's a mercury there, and we're going to hopefully add an oxygen. All right, we'll look at that. This reaction up here using B2H6, or more commonly BH3. B2H6 is the dimer, it's the same thing. But it's a boron reagent. The boron gives the anti-Markovnikov alcohol. This gives the regular Markovnikov alcohol. One thing we'll see that why these are down here is since there's no cation formed. Isn't there no cation formed here? What does Roman numeral 2 say? Yeah, since these do not involve a carbocation, there's no rearrangements. You see, H3O+ involves carbocation, it can rearrange. This often gives the same product, but guess what? It don't rearrange. You don't have to worry about it. So that's the power of this. All right, after that intro, let's cover it. White sheet. Oxymercuration, especially when you use water. If you use an alcohol, it would be called alkoxymercuration. Basically what I just showed you is you take this alkene react with H3O+, you actually get that alcohol over there, and that alcohol product comes from a hydride shift. It comes from a rearrangement. You should be able to envision that mechanism. If not, you should go home and work it right after class. Rearrangement. You do this reaction, though, with this two-step process, mercury acetate, that's mercury 2 acetate. Somebody told me that you don't see OAC in Gen Chem. I looked it up in your book and I believe it. OAC is acetate. That's O, like this. Okay? That's your acetate, man. All right? Certainly covered in Gen Chem, but you didn't see this abbreviation. AC is right here. Acyl. OAcyl. You got two of those, so you got two minuses, so mercury is 2 plus. Go look at this mechanism. If you do that, you get the sort of the standard product that you would have gotten up there, but no rearrangement. All right? You know, I can't take you through that top mechanism again and again. If you're not sure about the mechanism, you need to go through, work it, and see how you get the rearranged product, why this would be the product if it did not rearrange, etc. But if you use the oxymercuration route, it will not rearrange, and that's the product you'll get. So let's look at this mechanism. Well, the first thing to know is you've got mercury 2 plus. I mean, this you can just show it. You can show it a variety of ways. The book may show it differently. Maybe one of the acetates ionizes. I mean, the whole thing is ionic. So we could show it like this, with a mercury there and a separate acetate. Okay? In solution, this is probably ionic and it's really mercury 2 plus. But I just want a mercury 1 plus. Now the mercury 1 plus looks a lot like an H plus. And we know alkenes can attack H pluses. Well, guess what? They can also attack mercury plus. So basically, your alkene, I'll have to redraw it because I'm over here. These electrons attack the mercury. Now we're going to leave cation on the alkene on left or right? Left or bottom, correct? So we pull away from that carbon, attack the mercury. What does that give? The mercury is now bonded to which carbon? The N carbon or the second one? The N carbon. Electrons hinged away from that one and went and bonded to mercury. The N carbon is bonded to mercury. And we can show that acetate there. What's here? Well, we are under Roman numeral 2, but for now it's a cation. Okay? Now one thing we need to know is mercury does have at least one lone pair. Do it. And because it has a lone pair, what do you suspect is going to happen here? Back bonding. And it will back bond, and what will that give? It's going to give a mercury that's back bonded. It's got an acetate there. Now it's hard to keep track of charge, but here the mercury owns the 2 electrons. And it's neutral. Now the mercury only owns 1, so it owns 1 less electron. What charge do you think should be here? Plus. It's now a plus. We've got a bridge with a mercury plus. That looks a lot like a bridge with like a bromine plus. Bromonium ion? What do you want to call this? A mercuronium ion. A bridged mercuronium ion. At this point, you got water there, right? The water is going to attack this just like a bromonium. That mercury doesn't like being plus, mainly because of the strain. I mean, mercury doesn't mind being plus, but the strain here, which bond's going to pull more and lead to more partial plus on carbon?
Tertiary.
Just like with bromine. It's going to pull, this bond's going to be elongated more because this can take on more partial plus. But it's not a free cation. See, there's some back bonding here. So we have to show it like this. And this water comes in and attacks this here and kicks these electrons off. So here you go, mercury, take them. We know you didn't want to bond anyway. Take those electrons, what does that give? Hopefully you got some room. I'm going to move up here so we can see. Hopefully we can see here. We got this. Boom. Let's see if we can see. Boom. The mercury's now over here, acetate. What's now bonded to this carbon? Water. Okay, I'm going to actually draw it down because it's not really going to matter. And I hope you can see. If you can't see the shell. You can't see that? No? Yeah? Okay, at that point, we can take an H here and go neutral. This acetate's been watching the whole time. Okay? Acetate can take the H, these electrons can stay behind, and we can get that product there plus what? Acetic acid. Acetate with an H. That's acetic acid. And that's actually the end. That's end step one. End step one. What have we done? We used to have an alkene here, right? What did we add across the alkene? A mercury and an OH. What's the title, the top word at the top underlined? Oxymercuration. We added an oxygen to one carbon and a mercury to the other. Oxymercuration of the alkene. Pi bond attacks mercury. Back bond. Hey, what do we have to put right here? Do you think this is really an intermediate? No, that's NAF. Because as soon as the pi bond attacks mercury, what's the mercury doing? Back bonding. It's happening concertedly at the same time. This is our first intermediate, mercuronium ion. Water attacks it just like a bromonium ion to give like a halohydrin. That's in step one. Let's look at where we're going though. What do we need to do to get from here to here? This is the final product. What do we need to do? We got an OH on there. How many H's on that carbon? Two. Just like at the beginning. But how many on the carbon there?
3.
What do we have to do? We have to somehow replace the mercury with an H. Well, that's what this guy here does. Sodium borohydride. Sodium borohydride. This is a boron with 4 H's. What's the charge of the boron?
Minus.
How do you know it's minus? Well, that's good because sodium is plus. This whole thing has to be minus. Why is the boron minus?
Standard bond.
Based on total charge.
How many valence electrons does boron have? Where's boron on the periodic table? It's right next to carbon. Right to the left of carbon. 3 electrons. But here the boron has 4. So it's got 1 extra, so it's minus. Sodium borohydride. Sodium borohydride is a source of H, 2 electrons. What do we call this? Sodium borohydride is a hydride source. Why is it a hydride source? Because first off, boron, you can never make boron happy. It either doesn't have an octet and it wants electrons. If you give it electrons, well then it's got a minus charge and it don't want a minus charge. Okay? You can't make boron happy. See, boron says here, H, you and your 2 electrons take a hike. And when the H and the two electrons take a hike, what does the boron become? It just becomes BH3, which is neutral. So that's borohydride is like, here, HU and the electrons go. So ultimately, H and two electrons can go react with something. That's why it's a hydride source. Now how do we get home? We're not really going to do a full mechanism. We're going to show you some partial. We're going to call it a little bit of magic. It may be like this. These electrons attack the carbon, and these electrons, let's keep track of the electrons though. And these electrons come on to the mercury. It's probably not the mechanism, but I don't want to do something that we'll never see again. Let's do it like this. We did it like this. What does this give? H bonding to carbon. That gives final product. Right? Electron. What does this form though? We're going here, get final product. Now I got 3 H's on the carbon plus what? A mercury acetate. And what's on the mercury now that we can show?
Negative.
Well, what does this mean? Now it has a lone pair. And indeed it's what?
Negative.
Negative. Now, we've got our final product there. All right, that's the second step. That's what the sodium borohydride does. Now, the fate of this is, this will separate and give you mercury plus acetate, and the minus goes with acetate. Because if you can show it covalently, it goes like this. But here's what I want to show you at the end. What's the charge of the mercury here? It's neutral. Because if that's minus, this has to be minus. And if that's minus, this has to be neutral. This is neutral mercury. That's mercury metal. That's one of the problems with this reaction. It's a very good textbook reaction, but in recent years it's become disfavored because it produces mercury metal. And so industry doesn't like to use it anymore because of strict stringencies, and they don't want to be producing lots of mercury metal that they then have to dispose of very expensively. But that's called oxymercuration. The big important thing about it is you don't get rearrangements because there's no cation. You didn't see any carbocation up here, did you? See, that's not really formed. It doesn't really exist. I'm just showing you that on the board to do you kind of stepwise. All right? So if you do it up top, you'll get a rearrangement. Alkoxymercuration, well, if you just replace this with an alcohol, and you add an alcohol here, whenever you lose an H, you'd have an OR. You'd have an alkoxy. So that's just if you use an alcohol. Questions about the oxymercuration? You know, there's a bit to it, but mechanistically it's very similar to what we've seen before. And what you need to realize, guys, aren't most of the mechanisms very similar? In fact, most of the ones under room number 2 usually have the bridged. Mercuronium, bromonium. Okay? Look for similarities so you don't have to memorize 10 different things and never work for you. Just learn a few basic things. Question?
What happens to the sodium?
What happens to the what?
The sodium ion?
You can look, there's got to be a plus up there somewhere, I mean a minus somewhere. I mean, where's the minus at?
The acetate.
Yeah, I mean, you just put it right here. You know, make sodium acetate is an end problem. But the sodium is truly a spectator ion. I just didn't show it after the beginning. Okay, the other reaction is with the boron. The boron gives the alternative product. It gives the anti-Mercavnikov. And I just remembered, I think he's Russian. All right, anti-Mercavnikov. just saw some boron there. The first step here is just BH3. Sometimes you may see it shown as a dimer, B2A6. Same thing. There's also some fancy boron reagents like BBN. You see anything fancy like that? It all gives the same product. All right? If you see BBN, just consider it as BH3 and do your mechanism thinking with BH3. Okay, we got an alkene BH3. Number 2 comes next week. That's way down the road. I have some students wanting to say, well, this and this, and no. Number 2 is way after number 1's done. First is reaction with number 1, just BH3. What type of reactivity does BH3 have? Well, we got a boron. There's only 3 H's. No charge because boron's group 3. There's your 3 electrons. Neutral. But there is no octet, so the hybridization is what? SP2, trigonal planar. See, there's no lone pair there. With empty what? P orbital, yes. If you graph the hybridization, you'd see 3 bonds to H and then an empty P orbital. So is this reagent electrophilic or nucleophilic? It's electrophilic. It would like electrons because it wants an octet. Of course, then boron becomes minus, and then it gets mad at it because it's minus. But at this point, it likes an octet. So it would like electrons. Now the alkene is electrons. The alkene's walking down the road. It sees this boron with an empty p orbital. What the electron's going to do? Here I come. I like empty p orbitals. Okay. Now this is not a plus, but it's still electrophilic. Okay. There's an empty p orbital here that these electrons are essentially moving into. Now, if you want to learn more about the bonding of this to this, other than just saying it's bonded, that's that thick book, The Nature of the Chemical Bond. All right? But for us, we're going to say these electrons are going to break away and go bond to the boron, and we're going to get something that looks like, we're going to have plus on left or right.
Well, that structure isn't the same. It's intentional.
I just bent that up because I have the H here.
No, there's one more.
It's missing a carbon.
Okay, this one here. Do it like this. These electrons are going to break away, attack boron. N carbon bonded to the boron. There's 3 H's there. Because if we make cation, are we going to leave it on left or right? Cation here, correct? What's the charge of the boron now? It's negative, because it owns 4 electrons. It owns 2 for all 3. Does the boron have a lone pair? No. We got a carbocation here, but we're on the Roman numeral 2, so we shouldn't have this here. What happens at this point? Back bond from where? There's no lone pair. Here the back bonding is not from a lone pair, but it's going to be a hydride shift, because a boron with H's and a minus charge is a source of what? We learned in the last mechanism. Hydride. Yes. See, at this point, the boron becomes a hydride source. And guess what the hydride does? It breaks away and moves over here. Now this, if that's atom 1, that's 1, 2, 3. What do you want to call this? A 1,3 hydride shift. From the boron. Remember, before we did a 1,2. These 2 electrons break away, over here, what do we get? Boom, 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 boom. This is now what? BH2 and it's neutral. How many H's here on the second carbon? How many there to begin with? 1. There's 1 there, but how many there now? 2 H's there now. I'm not going to draw either one in. Although a lot of times I would draw the new one in. You want me to draw in the new one? I'll draw in the new one. There's actually 2 there because there was 1 there originally. Now there's 2. First off, and this is in step 1. What have we done to the alkene? We added an H and a boron. What do you want to call the process? Hydroboration. We just hydroborated the alkene. Hydrogen and boron now on the alkene. What? Why is it 1,3? Because if the H is on the boron, let's call it number 1.
Okay, this is called boron 1.
If that's 1, this is 2. It ended up on the third carbon, the third atom away.
So it's not associated with the carbonate.
No, it's not associated with it. It's from where the H, if the H was here and it moved over here, we'd say it went from 1 to 3.
Is that carbocation actually formed?
That's what we're about to get at. Do you think? Well, it's under number 2, so it should. No, because at the same time the alkene is attacking the boron. Now, my terminology, I say the boron throws something at the carbocation. What does it throw at the carbocation? Yeah. As the alkene attacks the boron, what is the boron doing? It's throwing that H. That all happens at the same time. Now, I bet your book will show you some fancy transition state where it's showing things like this, and a boron, and H. I don't typically show that. But if you want to see it, okay. That's the true, like, transition state. If you haven't noticed, I do things, I show you this NAF, and then I say, hey, it's not really formed. That's the way I do it.
Dr. Stevens,
But it's NAF.
we call that a 1-3 hydride shift. Does the actual transition move hydrogen from 2 to 3 and then from 1 to 2?
No, nothing moves here.
Okay. And how do we know that?
Well, that's a great question. I imagine somebody has probably, look in the literature, somebody has probably had like, you could have Melkels here or something, non-H's, and you get the same outcome. Probably, this is probably mechanistically been studied. Instead of H, do it with deuterium, which is just an isotope of H. And you can see that the deuterium ends up here, instead of one of the H's being here. So an isotopic experiment would help sort of prove that. Ultimately, beyond seeing the mechanism in your eye, you're not really proving it. You're just discounting the other possibilities. We don't have time usually to talk about how mechanisms were developed and proven, but those are all great questions. By the way, H.C. Brown at Purdue was one who really came up with the boron chemistry in the 1950s. He also, working with BH3, he also was the developer of sodium borohydride, which really did a lot in the 50s and 60s. It's a huge compound now.
Borax?
Do what?
Is that borax?
Sodium borohydride, the reagent we showed before. A.C. Brown, he died about 6 or 8, 10 years ago. He was at Purdue. Okay, that's in step 1. What do we need to do to get final product here? See, there's 2 H's. There's 2 H's there now. So that's done. What do we need to do over here? Obviously, we got to get rid of the boron. We're actually going to replace the boron with something. What are we going to replace it with? Sodium peroxide. We got to replace the boron with what? An OH. We don't have an OH on here yet. Okay, replace boron with OH. I mean, that's CH2B. We need CH2OH. Well, guess what replaces the boron with an OH? Hydrogen peroxide under basic conditions. Okay, so we drop hydrogen peroxide. We're not going to look at a mechanism for this. I'm truly going to call this magic. Okay? But what does it do?
With a J?
I like it with a J. What does the reagents do? What does the second step of the hydroboration do? Replaces the boron with OH. We're not going to do it because the mechanism is very unique and we'll never see it again. It's not worth looking at. We may show it in the book. Importantly, though, no change in stereochem. That is, if this was bolded or something, the OH would also be bolded. Alright? Just have that in your notes for later. Whatever the stereochem is to the boron, you just replace it with an OH and it's the same stereochemistry. Once we get to that. So the hydroboration mechanism you should know. Okay, it's very standard. This is an AF because as soon as this is concerted. It's not a back bond by a long pair, but it's actually a concerted hydride shift. This will be important with our stereochemistry though. I'll go ahead and mention it. We'll mention it later. This was a hydroboration. But if this was a side, is the H and the boron going to be on the same side or opposite sides? What's the title of the, say it, where's our outline? Purple, does it say it in there? It probably does. Concerted mechanism. A concerted syn addition. What does syn mean? Or cis? Same side or opposite side? Same side, okay? These, whenever it matters, are on the same side. Or syn. Doesn't matter in this example, but I'm just pointing it out now. Question?
Aren't there two hydrogens on the carbon?
This is the new one, though. The new one, the new H and the boron that we added across the double bond are on the same side. Why is it the same side? It's pretty straightforward. If this is the side, let's say the front, you're the boron, you sat on the front row. I'm going to make a bond to you. At the same time, you make a bond to the other carbon. What side? My bond is forward. What side is his bond going to be on? Forward. Because it came from him. Unless you throw a curveball and bond over on the backside. But it ain't going to throw a curveball. The boron's on this side. The H gets thrown in. It's on the same side. Okay? This boron is here. The H gets thrown in. This is the same side. Just remember that once we do this again with stereochemistry. Probably next week. Okay? Question? So in the end, this gives the non-Markovnikov alcohol product. Because if you envision carbocation, see, Markovnikov is based on carbocation chemistry. If you envision carbocation, you'd make carbocation there. And standard chemistry is water attacking there and thus oxygen there. But we didn't get oxygen there. We got it over there. That's the non-Markovnikov product, atypical. Hydroboration, oxidation gives the atypical. So this is oxidation. The magic step is oxidation. Okay, so there's a lot to both of those, but really it's not complex, it's just a lot. You go through it, these details are there. Let's do a couple at the bottom. Anytime you're predicting the products, you got two things. First off, a little bit of just prompting and memorization. Okay, we got an alkene with BH3 and a magic step. What's that going to do to the alkene? That's a hydroboration with a magic step, right? What's the product? In terms of just terminology.
Non-Markovnikov
Non-Markovnikov what?
alcohol product.
Yeah, non-Markovnikov alcohol. And we just spent 15 minutes showing how that happens. So if you were to show that product with no stereochemistry, it would look like there's the original. That used to be an alkene. Where do you want to put the OH at? Top or bottom? Bottom. Good. Where's the new H at? It's actually up there now. See, there's an H there. Where up there, there's no H. Okay. But that's with no stereochemistry. We have two substituents here in this tetrahedral. The question is, are these two groups, should we show them cis or trans? Why trans?
Because if the hydrogen and the oxygen are the same, then the method must be the opposite.
Exactly. So let's show this as a bold or dash. Your choice.
Bold.
Okay, if this is bold, how is the new H?
Bold.
Also bold. Because before this was an OH, what was in? It was BH2. And the magic step came along and replaced this with what? And when it replaces it, do you change any stereochemistry? No. So there you go. But back here at BH2, how does the BH3 add across the pi bond? Are these two going to be on same side or opposite? Same, because if the boron, if the alkene attacks forward, it makes a forward bond to boron. Here's the original alkene. And then the boron throws an H at the carbon. If this bonds forward, how's the other one going to be? The BH2 and the H have to be the same.
So is the methyl back?
Something has to be back. So the methyl is actually back because when that H comes in, let's say it comes in here. As it comes in, it pushes the methyl back. The methyl is back. But you got to keep in mind, usually we don't show H's. So if I get rid of the H, there is what we really want to say. Well, we also got to convert this to that. The original question is, are the two substituents cis or trans? And the answer was trans. That refers to the two big substituents. But the two new groups are cis. You see? Now, of course, you also are going to get what? Yeah, you're also going to get there, which is the enantiomer. And as we'll learn, in enantiomer, you switch all of your orientations. The enantiomer is the mirror image. And when you look in the mirror, everything is switched. If you don't believe me, go home and hold up your right hand and look in the mirror. Your mirror image will have the left hand. Okay?
All the reactions we looked at so far.
Yes. Yeah. That is, if there isn't an enantiomer, it will give the enantiomer also. H2O2 is just magic. It replaces the boron with an OH. Magic. We didn't look at the mechanism. You don't need to know the mechanism for that. But importantly, when it does it, there's no change in stereochemistry. Okay, what is this down here? This looks like what? Oxymercuration. What does oxymercuration give? Markovnikov or anti? Markovnikov with no rearrangement, so what's that going to be? This is just like if it was H3O plus with no rearrangement. This is gonna attack, where are you gonna make cation at? Top. Yeah, it's gonna give this here. This just gives that right there. And there's a new H down here. And because that's not a chiral carbon, there's not 4 different things there, we don't need to show bold or dashed. There's no chiral carbons here. Here you got 2 chiral carbons. Chiral carbons. Question?
Could the anti-Markovnikov work if the base was water?
If this was water?
Yeah.
I guarantee you there's probably water here because that's not going to dissolve. Well, even hydrogen peroxide is aqueous. And there's water there. Pure hydrogen peroxide is explosive. It's usually like 30%. There's a couple of miscellaneous things here. There's an oxymercuration sort of procedure if you want to read about it. This page here is a synthesis of a potential drug compound. You can read the first page. Every place I've handwritten, these are reactions that we will eventually cover. If not here, in organic 2, that's organic 2 reactions, Wittig. But I think there's a, what's happening right here? In making this is a multi-step synthesis right here. 9 BBN is BH3. We can just consider it BH3. It's just a unique boron reagent. BH3 followed by magic. If you look, the only thing's right here. This alkene is reacting. This is going to give an alcohol with the OH on top or bottom? It'll be top. Okay? There it is. With a new H there. There's a new H there. Okay? Go home, you can go through this and rationalize that that indeed would be the product. So they're doing a hydroboration oxidation there to get the alcohol. From there, they're turning this into an ether by making that O carbon bond. And SN2 will be covered doing that during test 3. There's an example of a oh yeah, I did have it written. A hydroboration oxidation. The other page, literature is very important. You can see how they were doing some experiments with different conditions. They actually used BH3. You can see what they're doing there. I'd just like to give you that so you can see some real research what they were trying to do here.
So for something like the last couple of questions that we covered, you're going to ask us to predict the product, not what the mechanism is.
No, it would be both. It'd be predict the product, but also you need to know mechanism. For that one, yeah, you don't need to know mechanism for the second step. The hydroboration step, you need to know the mechanism. But the other thing is, once we get into a little bit more complex examples and truly stereochemistry, your mechanism not only allows you to predict product, but it also allows you to predict stereochemistry. Because if you understand that we attack the boron and the H comes from the boron, you know that they both have to be on the same side. Okay? And so your mechanism does everything for you. That's why I ask you to learn mechanism. Okay? Then when you see something a little bit new, you can just tweak your mechanism and then I know the new thing. As opposed to just memorizing just 50 isolated things. And believe me, it might make it through with a B or C, but if you get a 2, you're just going to fall apart. You try to memorize. Again, like math. I should mention, I was thinking about making a change to the lab schedule for next week, but then decided not to, so I don't know if I told anybody. But next week in lab, you'll be doing polarimetry. Okay, we're a little bit behind here in lecture. That's okay. Most of the information is in the lab. You can also do some reading. You'll cover it in the lab before we cover it here, especially the Monday and Wednesday groups. That's okay. So next week is polarimetry. The other thing is the bromination lab that you're doing this week, right? Yeah. That report is not going to be due next week because we haven't even started covering Fisher projections yet, which is part of that report. I'm not sure when. I need to talk to the other lab instructors, but the bromination report will not be due next week for anybody. But it will be due the following week, and for example, the Monday lab, it will most likely be due the Monday you come to the lab that next week. Okay. I'll tell you more next week, but bromination lab is not due next week for anybody. Question? That is also trying to figure out what we're going to do there. On the syllabus, it's sort of a non-lab, but a SciFinder or something. Let me tell you that next week. Yeah, there will be something.
So does that mean we'll have to turn in both labs on that Monday? Like both labs, your lab?
I'm trying to figure out how not to avoid that.
All right.
For now, no lab due next week for anybody. Okay? We'll see. Let's see what we can do in the last 5 minutes. By the way, the other one is a worksheet, not a report.
All right.
Okay, there is one additional reaction. It's not on that summary page, I don't believe, unless it's at the bottom. Is it at the bottom? Yeah. It actually is at the bottom. It doesn't really fit in above. Very important reaction though. You take an alkene, you can react it with hydrogen, H2, hydrogen gas. This requires a precious metal catalyst. One of the easiest reactions you ever do, it's like bromination. You react this with Br2, what do? You add a Br to each carbon. If you're ever going to add an H to each carbon, we add an H to each carbon, what do we get? It's that. And the pi bond is now gone, we say it's now saturated. Okay, there's a new H on each carbon. Question?
So what do they define as precious metal?
I thought you were going to ask that. Precious metal. These would be the expensive ones in the mid-range here. Like platinum, palladium, rhodium, ruthenium. Those. Precious means expensive. Your cheap metals like iron and cobalt, they don't really do it as well or at all. See, the metals, they know they're good, and they charge for it. So, this is called a hydrogenation because you're adding hydrogen. It's also called a reduction because when you add H's in organic chemistry, that's a reduction. So you'll hear it that way. Hydrogenation of the alkene gives the what? alkane. Right? But see that simple terminology? Did you realize that was an alkane?
Yeah.
Okay, but it's simple terminology. The alkene gets hydrogenated to the alkane. 2 H's added. But we do have stereochemistry, and we do need to talk about the mechanism. Mechanism is not ionic. What does he mean ionic?
There's no partial cluster.
Think about it, all of our other mechanisms were ionic. That means the intermediates were ions. So we can call them ionic mechanisms. This mechanism is not ionic. There's no ions formed. Actually, the carbene mechanism is not ionic because there was no intermediate at all. The mechanism is shown on the other page. Let's look at that real quick. Accordingly, though, we have stereochemistry. Stereochemistry comes from the mechanism. The mechanism is sort of illustrated up top. The hydrogen sort of sits on the metal catalyst. Okay? Some books may even say the metal sort of breaks the hydrogen bonds and then the H's are sort of sitting on the metal. It's kind of what the circles are like the metal. The H's get attracted to it. Why? Well, that's a great question. Read about it. So the H is sitting on the metal. The pi bond approaches. It's got 2 faces because it's planar. And how I like to describe this is the metal then shoots those H's at the pi bond like darts. Shoot me 2 darts, one on that one there at the same time. Boom. And now they stuck there like a dartboard. But the important thing is, are they on the same side or opposite? They're on the same side. They came from the metal. The metal shoots you. I'm not going to do any arrow movement, okay? You're on the same side. Which was yours? Same side. That's important. So, over here where we have stereochemistry in our product, the alkane is now tetrahedral here and here. 2 new H's, we only get cis. The ethyl and the methyl were cis. Why? Because the new H's, which are both back here, are on the same side. And so if the 2 new H's are on the same side, the 2 existing groups are on the same side. You don't get trans. Question?
You have these listed as H2, which is a gas. So are these H2 or 2H?
No, it's H2. It's hydrogen gas. You have to have a tank. We have one upstairs if anybody ever looks at it. It's just a tank. It's an apparatus for shaking and stuff. Not trans. But of course, you would also get the enantiomer, where both of these would be dashed. Let's finish this up if you give me 1 minute. Over here, so we call this a syn addition. Same side addition. Plus enantiomer. The H's could come from the front, that'd give the enantiomer. If they came from the back, it would give this. We need to look at is this over here. We need to see how both of these would get the same alkane. In terms of what type of metals, here's some here. Only one of them. And one student that thought all 4 were needed. Only one, your choice. Okay, don't need them all. Palladium is probably the most common. Platinum, nickel is common. Think about this. If you were going to make that compound, you got to realize that both of these give that. Hopefully that's easy. Which would be more exothermic? Which reaction would be more exothermic? We'll answer that next time. Any questions before we dismiss? Well, a lot of times I like to introduce stereochemistry the day before we start. We don't have enough time to do that. But basically, we'll be hitting stereochemistry hard next time. You've got the yellow handout that I gave you, the outline, and then you also have an email I sent you of the written notes. Please be ready for stereochemistry next time. Okay, guys, we have lab tonight. Tomorrow.